Hi. So after having discussed some aspects of accretion disks, accretion onto black holes, and the solar wind and so on and so forth, let us now move on to a slightly different topic, that of shocks in astrophysical settings. Right? We have come across shocks already, of course, in fluid dynamics. We have, just to review, shocks are essentially mathematical discontinuities that are to be found in supersonic flows. In particular, they are a particular kind of transition from supersonic to subsonic flows. Remember, whenever we were talking about transonic flows, till quite recently, we were not talking about shocks, we were talking about a smooth transition from subsonic to supersonic or supersonic to subsonic. Right? But shocks, on the other hand, are a particular kind of transition. Okay? They represent discontinuities in the flow, and it turns out that shocks are quite ubiquitous in astrophysical settings. Okay? And so since this is a course on fluid dynamics in astrophysical contexts, we will investigate in what kinds of astrophysical settings shocks are to be found. Okay? And so turns out the answer is in many settings. Okay. For one, shocks are to be found near Earth, and these are the best observed shocks. Near Earth shocks. Okay. Shocks are also expected in accretion flows, in fact, especially in disk accretion flows. Okay, although we did not discuss shocks, okay, because I wanted to keep things simple. Shocks are to be found in accretion flows as well, and in supernovae. And this particular aspect is what we will discuss in some detail. Okay, but before that, I thought I would give you a very quick overview of what shocks are, and why shocks are interesting in astrophysical settings. Okay, it's not simply the fact that shocks are to be found. They perform a very useful role in astrophysics. They're kind of unavoidable. Okay, there have to be shocks in order to explain certain observations, and that's why we want to understand how shocks arise. Before going on, I would just like to tell you that these are the best observed shocks, right, and near Earth. And so these kinds of shocks are formed when you see here would be the Earth. Okay, and the solar wind is supersonic by the time it reaches the Earth. Okay, so the solar wind is essentially impinging onto the obstacle that is the Earth, okay, and that forms what's called the bow shock, something like this. Okay, so this would be the Earth's bow shock, and these are the best observed shocks. Okay, because you see you have spacecraft stationed here. Say this would be my spacecraft, those little sails and so on and so forth, and many times these spacecraft can actually sample both the downstream side of the shock, which would be here, and the upstream side of the shock. They actually go back and forth between the shock, and they obtain very detailed observations. Remember, what the shock is simply a discontinuity in all physical quantities such as velocity, pressure, density, all of these things, and there are sensors inside these spacecraft, and the spacecraft move up and down. Otherwise you never know whether the shock is there or not. They move up and down, and they sense that they actually take detailed measurements of the fact that there are large jumps in these physical quantities between this side and that side, and therefore you ascertain that there has to be a shock there, and then you try to figure out, well, why should there be a shock? And then you reason that that's probably because there's a solar wind which is impinging upon the Earth, and the Earth is a solid obstacle, and it forms a bow shock, much like the other very well-known example, which is that of a bullet or of a, say, very sharp object, a sharp nose object like this. This could be a bullet, or it could be an aeroplane, for instance, and when it's flying supersonically, it forms a bow shock ahead of it, and this would be a bow shock. So the Earth's bow shock is very, very similar to that, okay, is very, very similar to this, and hence in these kinds of situations, of course, you have, these are lab situations, and so you would have very detailed measurements on both sides of the shock, and you would be able to figure things out. In astrophysical settings, this is the best you can really do by way of actually measuring the different quantities like the velocity jump, the density jump, and so on and so forth. The Earth's bow shock is your best chance of doing so, because any other astrophysical setting, such as supernovae, black holes, so on and so forth, are too far. There's no way you're going to be able to send a spacecraft out there. Okay, whereas near the Earth, you can have spacecraft, and these spacecraft sample both sides of the shock, and they actually explicitly verify that there are jumps in these physical quantities, and hence you're able to confirm that there's a shock there. Now, going on though, this is really not, I would say that in astrophysical settings, it's one thing to sort of figure out that there are shocks, and that's a matter of some fundamental interest. But more importantly, shocks are very good agents for accelerating particles, and this is really, shocks are effective agents of particle acceleration, of or for, if you will, particle acceleration. And I'll explain a little bit about what particle acceleration is as opposed to heating. And so this is what I wanted to cover first before going on to supernova shocks. But the main thing I wanted to, bring across here is that really the utility of shocks in astrophysics is that of they are very good agents. Okay, the point is you observe accelerated particles, you observe indirect signatures of accelerated particles, and in a minute I'll explain what I mean by accelerated particles. And so if these particles are being accelerated so efficiently, you have to search for agents. Okay, who is accelerating these particles so efficiently? And turns out that shocks are natural agents. Okay, so then you say, okay, well, if shocks are natural agents, can we investigate how they are formed, and can we sort of draw up, elaborate, or to the extent possible, elaborate plausibility scenarios to figure out how these shocks are formed? Okay, so this is really the context in which we study astrophysical shocks. I should say astrophysical shocks. Astrophysical shocks are effective agents of particle acceleration. So the utility of shocks is here. Okay, they are very good agents for particle acceleration, and so this is what we will focus on. Now, what really do I mean by particle acceleration, right? Now, what I mean by accelerated particles, and these particles can be anything. These particles can be protons, they can be electrons, anything. Turns out that electrons are the ones which are most efficient radiators. So most of the time when we talk about accelerated particles, we are really referring to electrons. Okay, let me finish what I was trying to say. When I mean accelerated particles, I really mean non-thermal particles. I use this nomenclature because these two things are, used interchangeably in astrophysical. People sometimes say non-thermal particles, sometimes they say accelerated particles. They're one and the same thing. Now, what really do I mean by non-thermal particles? Well, particles that are not thermal, as simple as that. Okay, so consider, for instance, say a distribution function with either velocity or energy on the x-axis. For concreteness, let's just say velocity, and the distribution function f of v on the y-axis, and a Maxwellian distribution would look somewhat like this. Okay, so this would be, let me join this, and this would be, I'm not very good at drawing these things, right. So this would be a Maxwellian, a thermal distribution. Okay, thermal distribution which is peaked around some velocity, right. So this would be the root mean square velocity, and it falls off very sharply, it falls off exponentially, as we know. This would be a thermal or thermal slash Maxwellian distribution, right. Now what do I mean by non-thermal? Anything that is not this, really. In particular, what we observe most of the time in astrophysical situations is that there is very often a non-thermal tail. In other words, there is an enhancement at higher velocities. And since velocities can go either way, positive or negative, I will draw this here also. This is what one would call a non-thermal tail. Why tail? Well, you see, we are talking about the tail of the Maxwellian distribution. When you're talking about the highest possible velocities that can be expected at a particular temperature, you certainly find in many settings that there is a non-thermal tail. Okay, you cannot possibly explain this tail by appealing exclusively to a thermal Maxwellian. This is the rub. Okay, and therefore this is called a non-thermal tail, and so these are the kinds of particles that we refer to as non-thermal particles or accelerated particles. Okay, so this is the deal, and often these non-thermal particles the distribution function of these non-thermal particles is a number per unit energy. It does not follow a Maxwellian, it follows a power law, like this, where this is the index of the power law. Okay, so this would be a power law distribution of energetic particles. It would be something like this right here. This would follow V raised to minus alpha kind of distribution. Okay, so this is the kind of accelerated particle distribution which we hold shocks responsible for. Before we go ahead, I want to say one thing very, very clearly. Shocks are a fluid phenomenon, right? Whereas these particles that we are talking about, these are not part of the general fluid. These are test particles. Okay, so these non-thermal particles, these are very high energy. In other words, they form part of the tail of the distribution, whereas when we talk about the fluid, we are talking about this part, the low energy part. When we talk about the accelerated particles, we are talking about the very high energy part. Okay, and so the mean free path for these non-thermal particles is much longer than the particles which form the bulk of the fluid, and so they are not really part of the fluid. Okay, and we know this, when we talk about fluids, there are no particles, right? There's no meaning in talking about particles inside a fluid. The whole point of talking about a fluid is that you are smoothing over the particles and you're really talking about the continuum. Okay, so I want to emphasize this. These non-thermal particles, these accelerated or slash non-thermal particles are not part of the background fluid. Is very important. Okay, they are like test particles. So why is that? Well, because these accelerated non-thermal particles are very high energy, okay, and so they form part of this non-thermal tail, and the higher the energy, the longer the mean free path. So their mean free path is so large that you cannot justify them as being part of the fluid. So they are really, you really have to follow them in a particle wise nature. You have to follow them particle by particle. Okay. Whereas the background fluid would be these low energy particles, these guys, and the shocks and other things are mathematical they are discontinuities in the background fluid. Okay. So the shocks are a property of the background fluid. Okay, and they serve as agents to accelerate particles. And so the accelerated particles are essentially test particles which are sampling the shock which is formed in the background fluid. Okay, and so these test particles get accelerated, they gain more and more energy. Okay, and in many settings in astrophysics, you find that these accelerated particles have very unique signatures. And so what you are actually observing are signatures of these accelerated particles. Those are the real observables in astrophysical situations. So you observe these signatures of these very high energy particles, and you conclude that these are particles that cannot be thermal, they have to be non-thermal, and then you ask the question, well, how did they get to be non-thermal? Okay, you ask the question, how did they get to be non-thermal, and then you conclude that they have to be a scattering off of some scattering centers. We will deal with that in a minute. And so then you come to the conclusion that you have to have agents that are accelerating these particles, and then you ask, well, what could these agents be? And the answer is, well, one of the possible agents are shocks in the background fluid, and these shocks are very effective agents for producing these accelerated non-thermal particles. So I want to close this part of the discussion here, but I want to make this very, very clear that the accelerated particles are not part of the background fluid. It's almost as if you could think of the background fluid, so say the background fluid as some kind of, some kind of fuzz like this, say some blue colored fluid or something like that. Okay. And many times in this background fluid you might have shocks, but these accelerated particles are, if this is blue, okay, then these accelerated particles would be red, for instance. Okay, and the accelerated particles are not part of the background fluid. The accelerated particles are just one here, maybe one here. In the background fluid you have many background particles. Of course, that's the whole point, right? You have lots and lots. You take a little parcel of this fluid and you have maybe 10,000 background particles here. Whereas accelerated particles you're talking about, they are not part of the background. They are discrete, very high energy particles. The mean free path between them is very long. They are not part of the background fluid. So these are not part of background fluid. Okay, that's what I mean by this. And the background fluid is the fellow who forms shocks and so on and so forth. Okay, so now let us move on and let us ask about something called, so shocks are responsible for what are called diffusive shock acceleration, and we will discuss this in a minute. But even before that, the point is particles. How are these particles accelerated? The point is the particles which are these guys, these large fellows. Let me write this down. So these guys, right? So these particles collide with scattering centers, and the concept of these scattering centers is a little vague, I must say. What could the scattering centers be? Well, for instance, these scattering centers could be kinks in the magnetic field. Okay, so consider a magnetic field like this, which suddenly has a kink here. So this would be a magnetic field, and you have a given particle which is merely, you remember a particle, a charged particle likes to gyrate along a magnetic field, and if it has already a parallel motion, it sort of follows a helical path. But you see, it's merely following a helical path as long as it can smoothly follow the field line. But if there's a very sharp discontinuity here, then it is forced to change direction. To change direction. And at this point, this would be what a scattering event would be, because that's what scattering is, right? When you have a particle merrily moving along, it encounters some kind of a scattering center, some kind of a collision, and it abruptly changes direction. So this would be an effective collision, so to speak. Okay, so particles, they gain energy via collisions with these kinds of scattering centers. Okay, and so let the gain in energy due to a collision, these are inelastic collisions. Okay, let the gain in energy due to a collision be some beta, so that after each collision, the energy of a particle is beta times E naught, where E naught would be the energy before collision and E would be the energy after collision, and beta is a gain parameter. So these are all inelastic collision. Okay, but the point is, it's not as if, so you have a certain volume, okay, and with lots of scattering centers. It's not as if a given particle can keep rattling around and keep gaining energy, indefinitely. No, there's always a certain probability that particles will escape the acceleration region. Okay, that's because you see there are lots and lots of scattering centers like this. For instance, there can be many scattering centers like this, and so at each of these kinks, particles can gain energy, but at the same time they're also performing a diffusive random walk, and they can walk out of this acceleration region. This would be the acceleration region, and they can walk out of this acceleration region. So there is a probability P, which is of course less than 1, that of particle remaining within the acceleration region. So the acceleration region or collision region, if you will. Okay, so there are two things happening here. Number one, after each collision, there is an energy gain given by this, and the amount of energy gain in each collision is beta. But at the same time, after each collision, the number of particles is equal to n naught p. So n naught times p. So after k collisions, you see, the number of particles remaining would be n naught p raised to k, and p is less than 1, right? And after k collisions, the amount of a given particle would have, this is, well, okay, let me erase this for the time being. Since I have not written k collision, since I've written after each collision, I'll keep this as it is. After each collision, there is a non-zero, but less than 1 probability that particle will escape the collision region, and that's given by this. And after each collision, the energy gain is E is equal to beta times E naught. Okay. Now, after k collisions, what happens is the E is equal to beta raised to k E naught. Okay, so this is my way of writing beta, and that's not very good, and beta. Okay, and after k collisions, the number of particles left in the acceleration region is n naught p raised to k, where p is less than 1. Okay, now I eliminate k between here and here. I use k here, I take a logarithm, and I use the k here and I plug it in here. Okay, eliminating k, I get n over n naught is equal to E over E naught raised to minus alpha, where alpha is equal to ln beta over ln p. So here is what we were after. You remember that in our discussion of accelerated particles, I said that most of the time these non-thermal particles have a power law kind of distribution. In other words, they are non-Maxwellian. This would be a power law tail. Okay, and here is a way you could possibly get a power law tail. How is that? Consider a phenomenological acceleration region, and these test particles are sampling scattering centers. What would these scattering centers be? These scattering centers could be magnetic kinks like this, little kinks like this. There are lots and lots of kinks inside this acceleration region. At each kink, the collision is inelastic, and we will demonstrate how such inelastic collisions can come to be. And after each collision, there's an energy gain, beta, but at the same time, after each collision, there's a probability that the particle does not remain within the acceleration region. It escapes out of the acceleration region, so p is less than 1. Okay, so after k collisions, what happens is a given particle has, so beta is greater than 1, so a given particle has increased in energy. Okay, beta raised to k. So the energy keeps increasing. It goes farther and farther into the non-thermal tail. At the same time, the number of particles which are remaining inside the acceleration region becomes lesser and lesser. That is why you see here, the higher the energy, the lower the number. Out here, the lower the energy, the more the number, but the higher the energy, the lower the number. And that's exactly what's happening here. Okay? The higher the energy, the lower the number. And in particular, if you eliminate k between here and here, you get a power law kind of distribution. So this would be the number of particles as a function of energy, and this has a power law distribution, and the index of the power law is ln beta over ln p. So this is a quick sort of demonstration of how you could get a power law distribution of accelerated particles due to collisions with some sort of phenomenological scattering centers. However, I want to again emphasize that these accelerated particles are not part of the background fluid. We have not even started talking about the background fluid yet. The background fluid comprises of very low energy particles. You take a little parcel of these background fluids and there are many low energy particles. They are probably colored blue. Okay, whereas these particles, the accelerated particles we're talking about, they are very high energy particles. Say, think of these as colored red, and they are few and very far apart. They are not part of the background fluid. They are test particles which are sampling properties of the background fluid, okay, and getting accelerated in this manner. And so now, when we meet next, take up the next part of the course, we will discuss how shocks in the background fluid can serve as agents for accelerating these particles. So we'll stop here for the time being. Thank you.